Here we describe the contents of Taylor's theorem. We start with its main statement. Let f be a polynomial over the field f of degree at most n. Now suppose c is a scalar. We can then write f as a linear combination of increasing powers of the term x minus c with exponents going from 0 to n. The coefficients are given as d to the power k, that is the kth derivative of f, divided by k factorial evaluated at c. We move on to the proof of this result. Suppose g is a polynomial that is simply a power of x. So say g equals x to the power m for some power that's less than or equal to n. We now use the binomial theorem and we expand x to the power m as the sum of x minus c with c all raised to the power m. This can be written in increasing powers of x minus c with exponents from 0 to m. The coefficients are given as the binomial coefficient m choose j times c to the power m minus j, j being our index. However, we can simply calculate from the power rule for the derivative that the jth derivative of x to the power m is given as m factorial divided by m minus j factorial times x to the power m minus j. And thus we conclude that the jth derivative of x to the power m over j factorial evaluated at c is this same expression with x replaced by c. And c to the power m minus j, and don't forget that we have the j factorial in the denominator. That gives us the binomial coefficient m choose j. We have now proven actually that Taylor's theorem holds for the polynomial g equals x to the power m for any given power of x. It can be written as, from the binomial theorem, on the left hand side here, it's written as increasing powers of x minus c with index j from 0 to m, and the coefficients being m choose j times c to the power m minus j. But we just showed that these coefficients are nothing but the same coefficients that are described by Taylor's theorem, which is nothing but the j factorial of g divided by j factorial evaluated at c. We move on now to the general case of f being an arbitrary polynomial of degree n. So with coefficients aj and the index j going from 0 to n. Here we have that f can be written as the sum as j goes from 0 to n of aj times, we now replace x to the power j by the result for Taylor's theorem for single powers of x, such as g, as we just proved before. We know that x to the power j can be written, as we have just shown, as increasing powers of x minus c with index k and coefficients of the kth derivative of x to the power j on k factorial evaluated at c. We can now switch these two summands, and the reason we can do that is because the external summand has no dependence on k. That is the reason we can switch it. So we bring the external summand in, and we now write it as the sum as k goes from 0 to j of the kth derivative of the sum as j goes from 0 to n of aj x to the power j on k factorial evaluated at c times x minus c to the power k. We've simply brought these coefficients aj into the derivative and so too have we brought the sum, which depends on j alone and has no dependence on k whatsoever. Now we see that the derivative, that the expression aj x to the power j is nothing but f when we sum it over indices of j goes from 0 to n. So we write at last that this is the sum as k goes from 0 to j of the kth derivative of f over k factorial evaluated at c times x minus c to the power k. Mind you, there is a slight error over here. This term now, once we have switched this to sums, should in fact be c. It should not be j anymore. Sorry, it should be n. It should not be j anymore. And then we at last arrive at the proof for our result. This, once we bring the sum of j goes from 0 to n inside the k sum, then the k sum now goes from 0 to n and not just from 0 to j. Now we present a short corollary of this result. Let f be a field of characteristic 0 and f a polynomial over capital F of degree at most n. Then the scalar c is a root of f of multiplicity r if and only if the kth derivative of f at c is 0, and that vanishes for all k strictly less than r, and the rth derivative of f at c is non-zero. The definition of multiplicity, so we say that c is a root of f of multiplicity r if the polynomial x minus c to the power r divides f. We then say that it is a root of multiplicity r, and also that no greater power of x minus c other than r divides f. So now, using Taylor's theorem, we write f in increasing powers of x minus c with the appropriate coefficients. We split this into two parts with indices of k less than r and then indices of k from r to n. For the second half of the sum, we factor out the expression x minus c to the power r, and what we observe is that if the kth derivative of f vanishes for all indices k less than r, then this first sum vanishes. And so we immediately see that x minus c to the power r is in fact a factor of f. If that is only if this condition is met, that the kth derivative for k less than r vanishes of f. Conversely, if the kth derivative of f is non-zero for some k strictly less than r, then it must be the case that x minus c to the power r does not divide f. And this is because the powers of x minus c are independent of one another. For if one of the derivatives of f less than r, less than the degree r, was non-zero, then one of the terms in this linear sum of powers of x minus c would be non-zero. And so we will not have that x minus c to the power r perfectly divides f, because there would be a remainder. In particular, now we expose this a bit more and we flesh out the details. In particular, if f equals the product of x minus c to the power r times g, with the degree of g equal to n minus r, then we can expand the polynomial g again using the Taylor series as the sum of increasing powers of x minus c with index k from 0 to n minus r. And the coefficients are given as the kth derivative of g upon k factorial evaluated at c. This is just the standard Taylor's theorem. Now, we combine this with the definition of f by multiplying it with the expression x minus c to the power r. So what we have is that f is equal to the sum as k goes from r to n of x minus c to the power k times the kth derivative of g over k factorial evaluated at c, and replacing k. Now we can replace g so that we write this same sum as the kth derivative of f on k factorial evaluated at c times x minus c to the power k, with indices k going from 0 to n. This is by using Taylor's theorem on f, and the left-hand sum is by using Taylor's theorem on g. As there exists only one way to write f as a linear combination of the powers of x minus c, given that they are independent of one another, it follows that the kth derivative of f vanishes for all k strictly less than r, since these two summands need to match. We've proven that x minus c to the power r divides f if and only if the first k derivatives for all k less than r vanish when applied to f. But that's not enough. That's not enough to prove multiplicity. We also need to prove that higher power, that x minus c to the power r does not divide f. So suppose that x minus c to the power k does not divide f for some k strictly greater than r. Then we must have that the rth derivative of f is non-zero. Mind you, there's a second correction here. This k index should be k greater than or equal to r. So it includes r in this inequality. If any index k greater than or equal to r is such that x minus c to the power k does not divide f, then we must have the rth derivative at least of f is non-zero. For otherwise, if the rth derivative of f was 0, we could then conclude that x minus c to the power r plus 1 also divided f. Now, if any larger power of x minus c to the power q was to divide f, then we would conclude that the kth derivative of f vanishes for k less than q, and that now includes r. That includes the index r, and so we would have that d to the power f equals 0. So it must be the case, it must actually be the case that the rth derivative of f is strictly non-zero. Otherwise, we would have x minus c to the power r plus 1 dividing f, and that would mean that the polynomial f has C as a root with multiplicity greater than R. It could be R plus 1, it could be greater than that, but it is surely not R, and that would be a contradiction. So that brings us to the end of this proof. Thank you for watching. Thank you for watching, and please stay tuned for the next video where we discuss polynomial ideals.